All right, I think we can get started. Good afternoon, everyone. My name is Taylor Grosvenor. I'm the residential sales manager for Small Planet Supply. I'm excited to welcome you to today's webinar on water drop and droplet systems with Albert Rooks. For those of you who are new to us, Small Planet Supply, we are a dedicated North American company, dedicated to the mission of creating both classic and modern high-performance buildings. In keeping with this mission, Small Planet Supply provides building materials and mechanical systems for energy-efficient buildings. Water drop systems are manufactured in Tumwater, Washington, and available through our system distributors in Oregon, Washington, Idaho, California, and British Columbia. Our distributors are listed on the Contact Us page of the WaterDrop Systems website. Presenting today's webinar is Albert Rooks. Albert is the CEO of Small Planet Supply and WaterDrop Systems. For everyone attending, please feel free to post all of your questions in our Q&A section. You'll see that down at the bottom section of your screen. Answering most of those questions will be Ben Wong with WaterDrop Systems and Small Planet Supply Canada. Any questions that remain at the end of the presentation or would be better discussed live will be answered by Albert once we conclude that presentation. Today's webinar is recorded, so in a few days we will send everyone a follow-up email with a copy of the presentation and just more resources on how to find out more information about water drop and droplets. So with that, I'd like to hand the presentation over to Albert.
Great. Thank you very much, Taylor. Good afternoon, everybody. Thanks for joining. I will go ahead and kind of get started. So welcome to today's water drop central heat pump water heating plant discussion. There is some product updates and general discussion about existing projects and existing project line, and always the topic of central heat pump water heating for multifamily and other commercial building types. Questions during the process are just fine, and we'll do our best to keep up with them. And I've got a lot of stuff to talk about, so I'm just going to kind of keep moving. Water drop is an exciting project for our company, and it comes out of a long time of thinking about heat pumps, CO2 heat pumps, and how to tackle kind of a large wholesale change of domestic hot water heating in buildings across North America. And our goal, what we've come up with, is creating these packaged plants, these kind of simplified deliveries, and a company and a service built around those, where we can engage with our distributors on a project within our market area and support the distributor, support the customer, create a design that can be delivered to the site in one single package in a skid system. And then existing buildings, you'll see we have maybe a couple of options to handle existing buildings a little differently. But in any case, what we seek is to kind of demystify and make a simple way to design, install, and start up and operate central heat pump water heating systems for multifamily buildings in warm climates and cold climates up and down the Western US and Western Canada. So all of that activity means you just bring all the questions to us. We're really good for that. And we like to talk about sizing. We like to talk about how the systems work. And we kind of create this project partnership with our distributor, who we want to bring in very early in the conversation, because they're going to have the ability to know the local markets and local trade education level, who's installed systems before. So it's a good partnership to work out. All of this has come from years and years of research. We've learned a lot on the trail. The trail for us started when this wonderful heat pump from Sandin, or Eco2 as they're known these days, arrived in North America. It was brought in by a fellow named Ken Eklund, along with Sandin, the manufacturer. And it went through a whole lot of trials. And these were early days in developing central heat pump water heating systems. There were systems, but there wasn't really anything around a CO2 refrigerant. And so lots of research led us to understanding that CO2 is really special. It's a really good tool for water heating. And water heating, the unique thing about water heating as opposed to space heating is you really need these higher temperatures. And most of the refrigerant systems right now that we can use in North America struggle to work in even modest ambience and deliver higher temperatures in a single pass and get a really high COP. And if the ambience start getting colder and we get into freezing and below freezing conditions, that makes it really a lot harder on the refrigerants. So the one thing about CO2 is we can see on this chart, we can take and compress the refrigerant in an environment that's roughly 1400 to 1600 psi. And in that condition, it kind of crosses a threshold and it takes on a transcritical state or a transcritical form, which means it's all the density of a liquid, but it's still really in a vapor or a gaseous form. So in that condition, it's got a whole lot of temperature, right? It's just a hot compressed refrigerant. And if we push it along and we show that high temperature, high compression vapor to a waterside heat exchanger, which is actually acting kind of like a gas cooler, the energy just jumps from the refrigerant right onto that little pipe of water. So that's essentially what it is. And we get that energy transfer. So we can use a super efficient compressor to compress that refrigerant. And then we don't have any additional heat exchangers. We can just move that heat energy right onto the potable water system. And we get these really high COPs. And with CO2, it works in cold ambience, right? So we can go up to northern BC, certainly BC Canada is a very, very big province. And we can go a long way to the north, 12-hour drive from Vancouver, BC, and be in minus 30 conditions and still get a full 150-degree output temperature off of CO2. Can't do that with other refrigerants. That's really kind of challenging. So CO2 is a really super good tool for doing this. So now that we've got a refrigerant where we can run that system, it becomes, okay, we've got a tool where we can take a hot refrigerant and turn it into a hot potable water system. How do we actually apply that onto a building? And so we spend as a company a lot of time thinking about this. There's been a lot of thinking about setting up these systems here, primarily in the West Coast, where a lot of this thought is kind of developed. And really what came out of it is it's all about storage. We know that gas boilers, really if we need more water volume coming out of a boiler, we can just bring more water and bring more fuel, light it on fire, and we can get a really high recovery rate. Right? It's just a relationship of how much fuel we have available, and we don't really need a lot of storage. Heat pumps are totally different. The CO2 systems or other refrigerant systems work really well. We can achieve these high temperatures and in cold conditions, but we can only have so much throughput. So we design domestic hot water systems for these buildings based on storage. So we take the downtime when we have more heat pump capacity than load in the building, and we start charging up our primary storage. So the picture on the screen that we're looking at right now is a real building in Seattle. It was monitored across various conditions. And those peaks are just the morning peaks. It's standard market rate housing. And so when everybody gets up and starts showering and consuming domestic hot water in this multifamily configuration, that's what it looks like. So really all we got to do is design enough storage to be able to cover that peak from beginning to kind of end as it heads into that valley. And then, as we see later in the presentation, we can think about how many heat pumps or how much heat pump capacity do we need to kind of recharge that storage? And those are all just simple sizing questions. And these days, we've got a lot of really good tools to work through them. So as we move forward with these systems, in new construction, what we find and kind of the heart of WaterDrop is We've been in this picture a lot over the years, where we look at a building and we're going to customize a system for the building. So someone will step back, do a sizing, understand how much storage we need and how much heat pump capacity we need. And then there comes the question of where do we put it? Heat pumps generally kind of want to work outside and work on the ambience. The tanks want to store inside, and they take a lot of space. It used to be we could put all of this in a mechanical room down in the basement, but that's no longer really well suited to handle a heat pump system. So in this building in Seattle, new construction, just a few years old, the solution was to build the low-rise building, something around 6 floors, something like that. And then on the top of the roof, build another wood frame enclosure just to handle the domestic hot water system. So the picture of Peter walking out of that building, we were kind of there starting that building up and watching it kind of run. Inside is that picture to the left, all the tanks. And you can kind of see all the way back, there's a mixing valve, and all the way on the front, lower right hand, there's a red expansion tank. So there's lots of parts and pieces in that building. And then the picture above are the heat pumps. There's 5 heat pumps up on top of the roof of that building. So when you think about it, somebody had to kind of construct the building and then design the domestic hot water system, and then a box, and construct and develop that box. And then an installer had to go take all the equipment inside and start laying it out, and then put the heat pumps on top of the roof. And you can see all the piping is up there. You can also kind of see that each one of those heat pumps has a disconnect. And so there's kind of a lot going on. And that is the challenge, right? At this point, we're kind of at that point, like, we know we can make a building work, and we can do it with a lot of Sanco 2 heat pumps, or we can do it with a big Mitsubishi or other systems. We know how to do that. What we're looking for is to kind of move into a market transformation. So in a market transformation, you start asking questions about how can we take complexity out of the game, take risk out of the game for those who don't do this as a basis of their business, and do it kind of at scale. So what we came up with on our side, after consulting with policymakers and other folks in the industry, is a package solution. Really, if we want to be able to start moving buildings and install heat pump systems, we want to do it quickly. We want to do it well. We want to have these systems save the energy and function and not get any cold water calls or things like that. And if we can move it to a simple package that we can place on a building rather than a solution that we craft new for every building, then we're able to do a much higher adoption curve and get a lot more reliability and probably save some money in the process. So the packages that we came up with is a skidded package. And this skidded package on the screen right now contains everything in a system. So it's got a steel frame with a full seismic evaluation, so we can put it anywhere. And inside that, you can kind of see on the back that for us, there's Sanco 2 heat pumps. They're all ganged together and working together as one, which means we don't need a lot of redundancy. It's kind of this trick of using lots of smaller heat pumps rather than looking at a load and saying one big heat pump and then adding another level of capacity in case that big heat pump goes down. But along with those heat pumps, we put everything else. It's all inside that skid. So the big white tank in the back is primary storage. And this is for a modest sized building in this case. The middle gray tank is the swing tank, and we'll talk about what swing tanks do. All of these things have insulation within the box, and the box itself has another layer of R8 continuous rigid insulation all the way around it and protected from the weather. So we can place this box out on the roof, and later we'll look at some projects that have these out on the roof. You can see a big old red expansion tank down there in the front. You can see the building connections kind of down at the very bottom towards the front. An electronic mixing valve, always electronic mixing valves. They report data back to our controller, and we can kind of maintain that small delta T that we want. The controller is up there in the front in the head. And so this is entirely a heat pump water heater. What we don't see right now is a three-phase service panel where we land power. But essentially, if we put all the covers back on that thing, we set it down in a building, we land power, we connect 3 water pipes, and we're done. We just let it fill with water, start it up, takes a day to start it up, but then we're done and it's just going to operate itself. That compared to this is a challenge, right? This is a craft solution for every building. So someone's going to size the building, design a system for it, however, whatever tanks they use, whatever heat pumps they use, it's a custom design for every system because it's kind of laid out somehow on the building skin and the building envelope. And that is a whole set of labor and evaluations themselves. So we wind up, when we look at packaging versus kind of custom crafted solutions, we look at these 2 solutions right here. So these are 2 very similar building sizes or units or occupants. It's really how we look at it. The upper building is the one in Seattle. The lower picture of that big blue box is a water heater about the same size that is on that building that you're looking at the top. And we'll see that project later. It's in Fresno, California, and it's up and running and so forth. But when you kind of think about it, we made that lower box as a package, as a system. It's a single part number, a single submittal, and a single item for a plumber to install and bid on. Comes with a warranty. It's a water heater. It's done. So the cost position between those 2 transactions completely different. The parts are far less expensive on the above consideration because you're just buying parts. It's the labor and the design and the building enclosure that has all the cost associated with that, and it turns out to be a lot. So we'll take a step back here and we'll look at what it looks like in the shop as we produce these. So this was that picture that we saw of the system in next to the one in Seattle, sorry. And we pick up some cost reductions, right? So we don't have to step back at the building and create a new design to fit in that building. We've got 7 different models. We run a sizing and we just pick a size. Once we pick a size, it's a part number. It's already done. It's got a submittal. It's got a complete parts list. We know what it is. We've made it before in this case. And we just produce it in a factory. And producing it in a factory is, as we all know, is super efficient. Everything is uniform. We build everything out and design it in SolidWorks and then go to assembly. And we have great quality control and we're able to move around very efficiently. Forklifts are always available. We can crane things. It's just a super efficient way to do things. We're also able to kind of maintain some really good maintenance options because we use some really nice webstone valves on these, where we can provide some clean out. But in addition to the clean out, using multiple heat pumps gives us that ability to size the plant as it should be sized rather than sizing it and then adding some additional capacity to cover potential redundancy needs if equipment fails. In our systems, we use lots of heat pumps, and if one goes down, it doesn't really matter. It just makes the system recover a little bit longer. So we pick up redundancy, efficiency in that way, even though when one looks at it, it might be kind of a higher first cost, but there's a lot of value built in. So in addition to that, we do use those webstone valves I was kind of referring to, which makes it really easy for someone to take an annual maintenance trip around the plant, inspect it, maybe push some water through to descale, whatever the operation is. It's built with quality and they're all the same. So it becomes really, really simple for people to understand and our service contractors to understand. We also pick up some cost reduction just in the use of materials and are able to have a really, really compact design, because we'll essentially design the skid in SolidWorks, a full 3D view and render which kicks out a BOM, a bill of materials for us. And so we'll get a list of saying, hey, you need 6 pipes at 18 inches long and 50 millimeter diameter, and a list of elbows and other components. And then we just start pulling those components, creating the parts, and assembling them in the shop. It gets really, really efficient. And at the end, we're not customizing a power solution. We have our own onboard power landing. And so really when it shows up, it has UL or ULC or CSA if we're in Canada, right on the skid. And all we ask the installer just has the electrician bring single or 3-phase power, depending on the equipment that we're installing, typically 3-phase 208, onto the single power landing, and we're done. 3 water connections, 1 power landing, and provide some spots for condensate drain and things like that. So what we're really doing is providing kind of a full service water heater, just like it would be in a single family residence, where you go to a home center or you buy wholesale a single water heater and you take it to the project site and install it, fill it up with water and start it up. Same thing, just much, much bigger for much bigger applications. Everything's got pick points, so we can crane them up. That picture is a real job in Menlo Park. And those units are getting installed, and those are running now, depending on which ones they are. We'll see some pictures of the project on that one a little bit later. We've got to support this. So we've got a really strong West Coast presence that we've been building, both in the US and Canada. And then we've got some really strong distributors, I think kind of the best in the industry. In the Northwest, we've got Johnson Barrow, Osborne Company in Northern California, Olympic International in BC, Canada, and Flowtech for Southern California. And those are some really strong partners that are really all about helping people understand the project, how to implement a simple heat pump design, and how to get through kind of all the questions that are asked, and turn a design that's completed by an engineer and going to a contractor and then to an installing contractor, and how to make all that work without some of the drama that we experience in the construction industry. And I think we're pretty successful at that. So as we start looking at buildings, we want to understand what the building wants, what kind of sizing. So we use a lot of different tools. This is kind of the primary tool. It might be 4, maybe 5 years old now. It's called the EcoSizer. It was made in Seattle, Washington by Ecotope, funded by a number of California utilities who all pooled their resources to develop better sizing. Because heat pumps, whoever's heat pump we're talking about using, heat pumps are all about primary storage. And there's a couple of single pass methods and multi-pass methods, and having a swing tank and not having a swing tank. There's some variances there, but really a heat pump solution is about primary storage. And the way you understand primary storage in new construction is you've got to have some tools where you can say, okay, here's my building. I'm going to have an idea of how many occupants are in there. I've got a plan around that. I can kind of feather the occupant and feather it into the load by making some assumptions of market rate housing, maybe retirement, understanding and changing the occupancy rate per living unit, right? There's a lot of numbers I can change. And then I'm going to take into consideration what the outside ambients are, what the primary storage temperature is, what temperature I want to deliver water, 120, 125. And there are still more kind of decisions and influences, but that's a pretty simple tool. We can go in there and plug some numbers in, and we can come back with a pretty defensible sizing. And then we can step back and look at another piece of software, run a similar calculation, and compare those. This tool has turned out to be really trustworthy. We've done hundreds of projects, I think, in this tool, and really haven't had any cold water and haven't cold water calls, right? So no undersizing, and really haven't had any indications of oversizing. You get this information by looking at jobs that actually get installed and have an M&V system, and we've got a number of those. And an M&V system will tell you how many gallons are used per day and what the annual COP is and things like that. And so far, the data coming back is really pretty positive. So we as a company are really involved. Our distributors are really involved in using these tools. So we're always on board if somebody wants to bring us a building and start talking about maybe how to size. And then once we understand how to size it, then we know how to apply it onto the building. Buildings are changing a little bit, right? All the buildings are getting much more efficient. In our world, we're working with a lot of buildings that use very efficient ventilation equipment. Windows are getting better, air tightness is getting better, and all of these loads are being considered. And when you get into domestic hot water systems, you can look at a building and say, okay, I got a big building, it's got 400 occupants, it might be tall, skinny, or it might be a big California low-rise spread all over the place. Do I want one big zone or do I want multiple zones? Kind of what's the balance? And we see a pretty solid trend going to multiple zones, which is maybe not the solution for every building. In this building, it turned out to be a really very good solution because in each skid, so in this building, there's a lot of units and a lot of occupants. This is in Menlo Park. We'll see some pictures of it being built and started up and so forth. And it's housing some, the very smart software engineers in Silicon Valley. And in any case, when we step back and look at that building, the design was creating a vertical zone on a section of the building and having that served by one plant, and then another one next door. And so this building is being served by about 4 different plants that we can see. Each plant is its own skid. It's got its own heat pumps, primary storage, swing tank, control. It's got redundancy, and it's isolated from the zones next door, which makes it really simple. And as they're building the zones within the building, it's just a lot of vertical risers of smaller diameter with a lot less head pressure, a lot less surface area across the recirc. So we get a little less pump energy, we get a little less heat loss across the plant. Pretty nice, simple solution. And we'll see it in action. So when we start talking about sizing, we think about kind of how the plant works. And for us, and especially in CO2, our basis is a single pass. And a single pass means that we take cold water and we lift it to a high temperature, for us, roughly 150 degrees, and then we put it into a storage tank, all in one pass. So we create a design that uses the advantages of CO2 to be able to do that. So you can see that primary storage, that middle vessel, there's a little blue layer at the bottom, and that's the cold storage layer because we're using a stratified tank. And with a domestic hot water system, every time we take a gallon out and dump it down a faucet, a fresh gallon comes in. So every time we're consuming hot water, there's more cold water coming in and maintaining that stratification. And the only way that maybe we would lose that stratification is if we ran the recirculation system to the building out of that primary storage tank, out to the building, and then brought it back to that same tank. Because that act, when there's no load going down the drain in these overnight conditions, and there's a slide kind of after this that talks about it a little bit more, maybe this slide right here. You can see that on the right-hand picture, there's not a lot of load, right? Those little blue, the blue graph bars are kind of low. And so everyone's not pulling domestic hot water because it's late at night. And so that primary storage tank would start giving energy and returning energy. It gives energy, gets mixed down across the mixing valve, and then comes back maybe another 10 degrees cooler, and we start cooling that tank and we start mixing. And as we mix, we start losing that cold layer of water and that blue layer at the bottom. And so what happens is when people start waking up in the morning, they pull hot water out of the system and it starts getting replaced by cold water. But before that, in that condition, as the heat pumps start heating up, we're taking warm water out, running it across the heat pumps and putting it back in the tank. And that's the one thing about CO2. It's really, really, really good. It is the best at lifting cold water up to hot water in the conditions that we have in the industry right now. It just doesn't like to do it at 90 degrees Fahrenheit. So it's all about not letting that tank mix. And so we take that separate tank and we place that tank next to it. So now the primary gives to that swing tank. And the swing tank is giving out to the building across the mixing valve, out through the loop, and then returning back to that swing tank. And that way, all that energy, all that water movement and that energy loss that's associated with mixing down and losing a little bit at the building and then coming back to the swing tank is isolated away from primary storage. And primary storage now can maintain that cold layer of water at the bottom. Really simple concept. It's just a three-piece concept. And so when we have a condition that works like that, our relationships are the swing tank is really just all about the recirculation loop. And the amount of energy we put into the swing tank is really the amount of energy that would cover the amount that we would lose as we're sending it out, mixing it down, losing a little bit to the building, bringing it back. Sooner or later overnight, that tank will cool below our mixing temperature or approach our mixing temperature, and we just need to bring it up. So we just throw a few kilowatts of electric resistance into it, and it gets used occasionally over a 24-hour cycle just to correct for those losses. Next door, we still got a solid primary storage. It can hold a full 150-degree water. It still has a cold layer stratified on the lower section. And that primary storage, if we go back to kind of one of those first graphs in the beginning where we had that big peak in the morning, that's our primary storage. So we're just sizing our primary storage, kind of manage those peak loads so that we can get through the peak loads with storage. And then, we have to recover the primary storage at some point after we consume it. So then we move to the left and we look at recovery. And so the heat pump capacity is not like a boiler at all, where it's like, okay, I got a big building and I need, a big boiler. That's not what we do. We look at it and we say, okay, primary storage, average recovery time, what do we need? Maybe 4 hours, maybe 5 hours. It depends on the building and some other factors, but it's a number. So then if we say that primary storage is 1,000 gallons, then we'll look at a heat pump capacity and its recovery rate and size it to recover 1,000 gallons in 4 hours or 3.5 hours or 5 hours. It's a number, and we can vary that number. And if someone gives us a number, then all we get to do is step back and adjust the recovery rate or the heat pump capacity to achieve that number. So it's all doable. It's just approached in a different way. And so if we're building that system, building by building, craft by craft, it becomes complicated. These are fairly complicated things. But what our company does is takes all of that and puts it into a single package, saying, here's package 1 for small building, here's package 2 for larger, and on and on and on. And then we take that design, that set of numbers of how much storage we need, and how much recovery, and maybe what the swing tank volume is, and how many kilowatts we need to have available for that swing tank to lift based on what we see the losses are going to be. And then we just build it in the shop, create a part number, a full submittal, and there's a big water heater. So we literally turn these designs into actual product that's ready to go and just ready to connect to water and connect to power. We've got a lot of options and they're on our website. We've got a solid website. And both our company and our distributor partners are ready to kind of talk about any building. So you can bring a building to us. Some buildings we are probably a great solution for. And some buildings, you might look at it and say, well, I'm building an 80-floor high rise, and I don't want to create that many zones, so I'm going to do something a little bit different. But there are so many buildings that are just the sweet spot for our product range, that it just makes sense to bring them and talk about them, because it's so much more efficient and safer, and more doable, if you part the expression, to just look at a simple package system that's all engineered and ready to go. I see one question, WaterDrop compatible with BACnet IP? Yes, they are. We build and design our controls. There's more coming up on controls later in the presentation. And so, yeah, they can communicate that way, and a lot more now these days. So let's take a look at what's in the shop right now. We've got a standard product mix just on the shelf, ready to go. From as small as less than 200 gallons in storage up to 1,000 gallons, and 31 kBTU all the way up to almost a couple hundred, 185 kBTU. And these are all just systems that are 100% ready to go. You could contact a distributor today and say, oh my God, my water heater broke, I want one. And we could produce it and work with the distributor and get it installed, and away you go. It's simple. They're all configured in a very similar way. It's all a steel frame. There's a couple of lengths, and a couple of heights, 8 foot to 10 foot, depending on how tall the inner tanks are. And the skid lengths are roughly 11 to 12 feet. And they're all kind of a uniform. It's easy to locate them. It's easy to understand the weight. It's easy to secure them down to a pad or onto a curb on a roof. And as we start using up the capacity of one, really all we do is add a second one. We've created a system where these two skids work in the shop, and we'll see these two skids on a building a little later in the presentation. And that's the full water heater. And that works for this particular zone, and in this particular project has extra storage capacity per the zone, so it can do some demand response, because it's a California project, and California is heading the direction of having a little extra storage and doing this kind of load shaping where we can turn off electric appliances between 4 and 10 p.m. and do things, and they're offering incentives to do that, and we can 100% do that. And so in addition to a standard system where we embed the swing tank and the recirc pump and the mixing valve, because it's a whole water heater, into the system, we also make part load systems. And part load is a concept that came out of some larger developers in Vancouver, BC, where we're in a market, and we've got a building and we want to decarbonize the building. So it doesn't mean that we're going to change out the boiler and do 100% switch to heat pumps. We're just going to target a 75% reduction in fossil fuel use. So we can size that building, we can work with a budget, and then we can employ one of these existing systems to say, okay, our goal now is to pick up 75% of the daily load through 100% heat pump energy. So you can do that. It's been done. And there are other systems, or there's other needs and other applications where you really don't need a swing tank and recirculation loop, especially if you don't have a recirculation loop. And then for existing buildings, we've done a lot of work on this in the last few months. We've created the droplet product range. And essentially it's separating the heat pumps away from the tanks, because existing buildings are tricky. They're just all different shapes, and some have parking lots, some have flat roofs, some have pitched roofs. Existing buildings, everybody's used up all the space they're ever going to give. They have tiny little mechanical rooms, and you can't put these heat pumps in mechanical rooms. So you just need a system that's as plug and play as you can get, but is really, really flexible. And so we've designed a system, and the heart of the system is kind of the new, jumped a couple of slides, is the heat pump racking. We just spent a number of months redesigning the racking. You wouldn't think that racking was so important, but we created a new design that's expandable and has full seismic evaluation. So it's a design that we produce in-house, and it is now, after months of work, ready to go. And so we have a number of different configurations that are shown on our website, and our distributors can kind of help you sort through kind of how big you need. But you can get a lot of different sizes, and this is all recovery. So when we step back and we kind of remember, we look at that system saying primary storage, that's what's covering the peak. Swing tank is handling, kind of the recirculation losses and keeping the primary stratified. Well, the heat pump rack itself is really just the recovery number, and that number can vary. And so essentially what this design is, rather than skid it all together, we take all the complicated bits, join the heat pumps, control them, power them, arrange kind of the right piping, which is its own special activity, and we place them on a seismic rack with a power landing and put them outside. And then somewhere inside, we can place the tanks, and all we get to do is pipe in between. We've got some distance limitations that we've got to work with, but it's a really simple solution. And it's a lot more reliable than trying to design and install one in the field, start it up and make it work. Another improvement that we made in this round, and it's important in the droplet range, is that all of these things have their own built-in master staging controller. And the master staging controller does a lot. There's no way I could cover it all. I can't even remember it all. But essentially, you've got multiple heat pumps across different conditions, and you've got multiple tanks or multiple conditions. And now you're heading into an era where you want some demand response, and you want to broadcast out some information that becomes available on the condition of the plant. All of that is built into our controller. And it's the development of years around working with heat pump water heaters and kind of the questions and the things you want to know. And so we've designed a new set of landing panels where we can bring single phase for the smaller and 3-phase for the larger droplet racks, and built the control, which used to be in a separate box, right into this power landing box, and then brought the control visualization out onto the front of the box so you don't have to open it up and be exposed to high voltage power. And so that's all a brand new panel, comes with every droplet. And in certain configurations, you can work with our distributors and we create some very special projects. Like we have one in Vancouver, BC going on right now, where it'll use 3 different racks. And we develop a control scheme that controls 3 different racks with 3 different power landings. So it goes in simply, and then we just plug a Cat5 cable into each, and then one controls them all, just like it's one plant. Cold climates, it comes with heat trace and covers just a number of different sizes. And so all of that's really exciting for us. We produce centrally in our Tumwater, Washington plant. It's a new endeavor that we set up after the years of research and working with various partners. But it's all made, and we're all here. And then we do some additional manufacturing in BC now. And so when we bring these products in and we assemble them in a shop, we just get to understand kind of how they go together, spend a lot of time, go through process improvement. It's not like developing something on site. And spending all the time that it takes to do that. So building our own controls, writing our own programs, and multiple skids get connected by jump piping and low voltage connections. Everything we're able to go through, everything through a full QC before it leaves the plant. And they're really easy to handle. They've got forklift pockets and they've got crane pick points. So forklift them up, put them on the back of a flatbed, send them down the road, and away you go. The installer screws it down and gives it power, and we're ready to show up and start them up. So at this point, we'll take a quick little pause and we'll start looking at some existing projects. This one is in California, and this is right near the Menlo Park Facebook headquarters and all of that. And it's a rather large collection of multifamily buildings. So it's that building that you saw kind of the rendering of earlier with multiple plants on top of it serving multiple zones. And these plants have the capability, the last two of these multiple plants do have full M&V and load shift ability. It's one of the first projects in California that has full on ready to go load shift, and that will all be running trials on this project. But it's a simple install, and the installing contractor has been great to work with. They're just really surprised how well it's gone. They just built the curb and then craned them in place, and we showed up and started them up. Product quality is great. Application's wonderful, and it's easy to size up. Essentially, we're just validating a lot of information, filling them full of water, washing some water through some points so we can remove any construction debris that might have developed within the risers and things like that. And then once we feel like it's all clean and all the air's been bled out and so forth, then we can move to just engaging the heat pump, starting the controls and verifying the leaving temperature and the returning temperature, and recording values, electrical values and amp capacity and things like that. And then boom, you've got a plant. Takes about a day to do that. But that's just pretty amazing. This was another project in California. This is a 140 suites, a retirement building in Central California around Fresno. And it used to have a couple of boilers, and you can see that red line going back in the back of the building towards that gray vertical pipe. And that's the water connection. They trenched it in and inserted that water connection back into the building there on the second floor, and that's where the water enters. So this is a big water heater. They poured a pad, set it next to the building. I think our learning on this is that we want to offer more colors and maybe color match buildings and things like that. But this big bright blue water heater is working just great. We built it, put it on a lowboy trailer and sent it down, and then it was set in place. And the whole process took 3 days. One day was just receiving it off the truck and getting it off the pad and bolting it down and getting it all kind of ready and then full of water. The next day was our team going through doing the startup, which there's 2 of these, so it took a day to do 2 of these. Fill them full of water, check them, do all the air bleed and get the controllers working and start them up. And essentially on day 3, they turned the switch and the building was on heat pump water, no more gas boiler. This was an AEA project. They did a presentation on it there a couple of weeks ago by Nick Young, I believe, and he said he's, has lots of years of doing new domestic hot water installations in heat pumps, and he's never seen anything happen in 3 days. He just said it's the fastest thing they've ever done by a country mile, end quote. So it's a really successful system. It shows that we can just size, produce, set, and start up and turn the switch and the building's on. So we've got some new developments and new product lines that we're thinking of that are going to be active in 2024. Won't be able to cover all of them today, but essentially we're starting to look at water heaters now that they're an electric appliance and they're using kind of a precious commodity that the utility wants to control. We're looking at these as now thermal battery, thermal storage, and an appliance that we want to learn more about and control. The current demand right now in California for sure, and other markets coming on, it's different in the Northwest than it is in California. It's more about the Columbia River and salmon and just kind of where to place renewable energy. And in California, it's more about where when we're using energy and avoiding kind of the high peak and softening the grid and shaping the grid. And so essentially with water heaters, right, the water heater is kind of the one device that's always going 12 months out of the year. And it's got a solid, steady daily load. So it's got a solid consumption of fuel. And so the more you learn about it and the more you tweak it, the more you can kind of manage its fuel consumption, which might relate back to load on the grid, but could also very much relate to price to the customer. Because now energy pricing changes across the day. So in any case, in short, kind of what we're doing now is adding multiple thermistors across multiple tanks and really expanding out our control logic and how many IOs that we can use and what information we're going to collect. And so now our new versions are collecting a lot of information and managing these tank arrays more like a thermal battery or more like your cell phone battery, right? You can look at it with these multiple sampling points. You can start looking at it and saying, I'm 25% charged, 50% charged, 75% charged, a lot. And so once you start looking at a state of charge, it presents two things. State of charge says, well, here's how much I can endure without adding more thermal energy in, i.e. running the heat pumps. Or the other side is, if you're in a period of abundant electricity, you can look at your tank array and say, well, here's how many more kilowatts I can actually turn into kBTU and store in the tank, right? So it's kind of a two-sided coin. And then there's a whole bunch of other stuff kind of going on about sampling time of use pricing and developing the ability to kind of buy energy and store energy when it costs the lowest amount. So all of these things are possible through information. And so our next piece of work, which will be available in 2024, creates systems that we can treat these things quite a bit differently. The work is not yet done. We can't price it. We think it's a modest impact on our existing pricing. But in many areas, it opens us up to utility incentives, because the utilities are really all about kind of creating this marriage of use between manufacturer, end user, or building owner, and the utility to help manage the grid as all these new demands come onto the grid, right? So you can start thinking about, we charge cars here and we heat water in this time zone, and then we do these other tasks, right? So it's all about managing. And these days, we know how to get the information. These things are electric appliances, and we can build really smart equipment. It's just, you just never would be able to do this in the field, right? Because in that tank array and in all these configurations, we have to really understand where everything is and how it's functioned, and a lot of data points that's going to impact the logic behind this. So it's another case where we think we're building something that is worth a lot more than simply taking a bunch of parts and putting the parts together and then turning them on, and hey, you got hot water showing up at the end. You got hot water showing up at the end, but then you have a whole lot more potential, and you're able to do that at a compressed cost with a longer, maybe a longer warranty period. So in any case, that's a function of kind of where we're going and where we hope to be early or mid 2024 for plants that are delivered. Usually it takes a while to get through kind of the selection of the building and what plant we're using and so forth. So we'll always have that capability of it's more about information management than it is about, how big our tanks are and how many heat pumps we're using, right? So we can actually kind of convert projects along as the new technology becomes available, because it's more really about technology and process building. So with that, I think I'm ready to open it up to questions, and perhaps everybody's a little sleepy and there are no questions, which is okay also.
Yeah, it looks like Ben's been keeping up with the questions, so looks like he's just finishing up with one right now.
Wonderful.
Let's see. I don't want to end the presentation while the questions being answered. But thank you, Albert, for a wonderful presentation. Just as a reminder for everyone that this webinar has been recorded and everyone will receive a copy of the presentation, as well as some more WaterDrop resources in an email sometime next week. We just need to button up the file and make it pretty and send it on out.
Yeah, you're most welcome, Taylor. It's just really everybody. We're always happy to talk about buildings, water heating, sizing, installation, and just everything about that. And we've got really strong distributor partners that like to talk about the same things. And so we all want to work together and find solutions on how to really decarbonize water heating for larger buildings as risk-free and effortlessly as possible.
Wonderful. All right. Well, again, thank you, Albert, for a presentation. Ben, thank you for your work. Oh, well, hey, we got a question. I think we've got time. Albert, do enclosed units have to meet local building code requirements? Is there a risk of them being considered confined spaces?
So far, our experience is that they are a single part numbered appliance. And we have not had any of those funny issues. I suppose I should just say no, but I always kind of consider things and the impact. So no negative experiences like that. And really the industry and the municipalities are just looking at a water heater. And the questions are, plumb correctly, materials, electrical connection, and where we use a electric water heater inside is the swing tank. We have an access panel that is clearly labeled that high voltage is behind this panel, and it meets kind of that fire department requirement of 3 feet wide, 3 feet deep. And so they are designed to just go right into a building and be inspected as a single unit.
Thank you. All right. Well, it looks like we had a two-parter from Phoebe. One answered and the other one's still opening. So why don't we start from the beginning with this question? Do the 318-gallon tanks go onto a single skid with a heat pump water heater and swing tank? Sounds like the approach would instead be multiple skids and zones. And there is a question of access to internal components.
Okay, so there you go. Great question. So that would be three roughly 300-gallon tanks. The one on the right in this picture has got that yellow sticker. Right behind that panel is the swing tank and the electrical connections. And as far as access goes, all of those panels are removable. So the way that they're serviced is each one of those panels that we're looking at, including the side panels on the end, are all removable, not the one with the high voltage on the left, but we're designed so that you can take off two of the sides and have full access, replace tanks, do really anything you want, and the roof comes off. So to get into one of those panels, it's 8 bolts and the panel comes off. The panel is kind of got a vertical joint that's kind of like commercial roofing, where it's a V groove sitting on a V groove that channels the water away. Hope that answered it.
It looks like it does. You got to thank you.
Yeah, great.
All right. Well, we're right at that time. So again, thank you, Albert. Thank you, Ben. And most importantly, thank you everyone for logging on and being a wonderful audience. If you have any questions, do feel free to reach out to us, and also look out for that email headed your way in a few days. And with that, we can all get back to our afternoons.
Everybody have a great day. Thanks very much.
Thank you.